Right.
Donna, soon, array, and yes, we're down to 9.
Thank you.
Huh?
Why did you keep more?
No,
it was you. I know it was you.
It wasn't me. I don't have that power.
Thank God.
Yes. Yes. All right. Next lesson now. Okay. Just before I start, Todd, you were last week asking me about Lorentz force. Wasn't it Lorentz force you were talking about? And actually I looked that up, it's nothing particularly special. You remember we did this formula for force on a charge in an electric field, and then we did this formula, QVB, for a charge on a, no it's not actually, for a charge on a particle in a magnetic field. Lorentz force is actually both of them added together. That's what's called the Lorentz force.
Well, I learned this so that it's just QVB.
Well, I mean, technically, it's both of them really. That if you had a charged particle in only a magnetic field, then this is the Lorentz force. If you had a charged particle in an electric field, this is the Lorentz force. And if you had a charged particle in an electric magnetic field, it's both of them together. So Lorentz is for both. Okay. So what we're going to have a look at now is induction. Okay. Joshua causing trouble?
Yeah.
It's his nature. It's difficult for him not to.
Joshua, can you sit in the first right? No.
Try not to shake the table, alright? Okay. So induction. This is when we create an electrical current. Okay, so when a conductor is placed in a magnetic field and the field changes, its magnetic flux, which is magnetic flux density or magnetic flux. When it changes this, then a current will be produced in the conductor. So in fact, if you had a conductor in a magnetic field and you made the magnetic field stronger or weaker, then you'll have a current running through the conductor.
Could we say it's the distribution of electric charges or electric current due to nearby charges?
What do you mean, say again?
Should we say it's the redistribution of electric current due to nearby charges?
You're not mentioning the word magnet though. Could you say that again by mention magnet some way?
The redistribution of electric current in the magnetic field due to nearby charges.
Feels a bit shaky, I don't know. If you have some different definition, if you can find this for me, I can have a look at it, okay? So, what happens here? Can I scroll down? Imagine now we have our magnet. So I'll just draw it like this, north-south. And we have our conductor, which could just be copper wire or whatever, anything. If this magnet was then moves away really quickly, then what you'll find is you get a current running through the conductor. So, basically if you have a magnet and you move it over a conductor and take it away and you put it there, in other words, if you keep changing the magnetic field around the conductor, you can make a current run through the conductor. Okay? And this is called induction.
But doesn't it depend on the strength? If you do this constant.
Oh yeah, it depends on, we haven't done the formula yet, but yeah, it depends on the strength, of course. Depends maybe on how quickly you're moving it. Yes, of course, yeah. But the key, the concept I want you to understand is that a change in magnetic field will cause a current to run in a conductor. And this is called induction. Okay. Now, maybe I can draw something here. Can you scroll down? Okay, so here's our conductor, and for E is, let's say, here's our, I'll draw it a bit smaller. Here's our magnetic field, just like this. And let's and this is the magnetic field at the beginning. And then let's say, however I do it, I make the magnetic field stronger. Okay, so the magnetic field maybe 1 second later gets stronger, so it could look like this. So which way is the magnetic field increasing? It's increasing to the right, isn't it? It's getting bigger as it moves to the right. Yeah?
The arrow represents magnetic direction of magnetic.
Yeah. Yeah. Sorry, I should write that in. This is the magnetic field, and this is the conductor. Now, the magnetic field is changing, and its change is positive, as in it's getting bigger as it moves to the right. And if the magnetic field was getting smaller here, its change would be negative. It's like it's slowing down almost. Okay? Our first law we're going to do is called Lenz's law, which says that the current you get in the conductor is always opposite to the magnetic field. So in fact, in this picture here, the current would run opposite to the magnetic field, like this. Which is which one?
Basically, the faster we move the magnet, the more voltage.
Yeah, I think that's called Faraday's law.
Oh, yeah, Faraday's
Yes, yeah. So that's what we're going to do next. So this is our first law. This is called Lenz's law. The current produced will move counter to the magnetic field. That has an important safety result, which we'll talk about in a moment. But just before I do that, we have to talk about the opposite here. So remember last week we did DC motor and AC generator. So with a DC motor, what we had was, when you had a current in a magnetic field, there's a force, and the force made the wheel turn, remember? And then with an AC generator, when you had a conductor in a magnetic field and you apply the force, then you make a current run. Okay? So these things in fields, they tend to go in pairs. So this one here is, if I have a magnetic field I can make a current. But the opposite is true. When I have a current, I can make a magnetic field. Okay, so I think this one is called, this is, if I remember correctly, the right-hand rule, another right-hand rule. But if you have a current, you put your thumb in the direction of the current, and you curve your hand, so it's like this, okay? I think it's right hand. Yeah, you put your thumb in the direction of the current, and the way your fingers are curved, that's the way the magnetic field is moving. Okay, so in this picture here, if the current is going that way, I'll have a magnetic field produced around the current going, well, you can't really see it here, I'll try and draw it in 3 dimensions somehow. Current going that way, and then current going,
you could just draw the way you draw this one.
I'm trying my best here. The current is going this way around. This is using the right hand rule. Okay. But do you think this is true for all currents? What do you think?
That there is a magnetic flux on an all current.
Yeah. What do you think?
What do you mean by all currents?
Like DC or AC? If we look back for a moment here, this one says when you have a change in magnetic flux, you cause a current. So, do you think here if I have a normal direct current would make a magnetic field?
No.
I don't think so. It would have to be an AC current. That if you have a change in current, you can make a magnetic field. Because if you notice in this one here, it's important that this is changing. Then you can make a current. But in this one here, if this was just direct current, it's not the same thing. There has to be a changing element to it. In other words, what I'm saying here is, if you have a change in current, then you can make a magnetic field. Which we saw already, that's AC. Do you remember AC current? This is a current that gets stronger, weaker, stronger, weaker. Okay, yeah? So in other words, AC current can produce a magnetic field. Now it said that this has an important safety consequence, which I'll talk about now. Okay, can I look at the safety example? And I'm sure you have these at home as well. If not, maybe you've seen them here. But they're the extension wheels for if you're working in the garden or whatever. They look like this. It's a cylinder, and it has 2 plugs on it, usually. And there's a cord wrapped around it. And then this connects into the house. So what you do is, you plug your lawnmower or whatever into one of these. So this goes into the garden then. And what you do then is you can wheel this, you can unwind this so you can get out more cable. That's the extension cord, yeah. Do you have one of these at home?
Yeah.
Yeah. Now, this rule we're doing, Lenz's law and induction, has very important safety consequences for this. If I draw this again, but maybe just a little bit expanded. So what you have is, you have your current. Oh, by the way, it's AC current, because they're all AC currents in your home. And it's going around. Now I know it's going around, but I'll just draw it like this for the moment. And then it goes out to the garden here. Because this is AC, you get a magnetic field around this. Yeah? Now look what happens here. You get a magnetic field around the top wire. This magnetic field is changing because the current is changing. But what happens to this conductor underneath the first wire? This conductor is inside a magnetic field which is changing. And what happens when a conductor is inside a magnetic field that changes? It produces a current, doesn't it? But Lenz's law says the current produced will be opposite of the magnetic field. So in other words, what you do is you get a current here which is counter the current that's going into it in the first place. So in other words, what I'm saying is, here. So here's my wire. So let me we can imagine it's wrapped around in the center, okay? So it's something like this or whatever. So the current is coming in here, because it's AC, it's changing its magnetic field. And the magnetic field here in the center is changing. And this piece here is also a conductor. It's inside a magnetic field that's changing, which means it gets a current in it too. But there's already a current in it, isn't there? The original one here that's going through it. So now you have two currents. But this current that is produced by the magnetic field is produced in the opposite direction of the current that's running through it. So what do you think the consequence of that is? The current reduces. In other words, well, this is a scarf. I can't draw the wheel diagram properly. The current that's produced in the extension cord will be produced in such a way as to be opposite the current going into it. This is not an extension cord. I'm just trying to give you the key idea here. But what do you think happens when the current cancels the original current? What do you think the consequence of that is? No. I mean, you have current going in, or voltage going in, and then some of the voltage is reduced. So that means some work is being done. But what work is being done? Heat. Yeah. So what will happen is your extension cord will start to heat up. And you'll notice if you look at your extension cord, there's a safety sticker at the back that says, if you are using high current appliances, you must make sure the cord is fully unwound. Okay? So the next time you're at home, have a look at the back of the extension cord. There should be a big safety sticker on it that says, if you're using high current appliances, make sure it's fully unwound.
For the extension to be unwound, or
the wheel to be fully unwound so that there's no wire that's looping over itself. Make sure the wire is fully extended out. Now it's only a problem when you have high current, because if it's a low current there's not much of a magnetic field. Yep?
I'm confused. The current, the source of the current is AC.
Yes.
It's from the socket.
Yep.
That's the first current.
Yep.
And the second current is due to...
It's due to the magnetic field caused by the source current changing. So this is actually called self-induction.
Yeah, okay.
Do you know what I mean? Self-induction? The current itself is causing another current later in the conductor. It's interfering with itself. You can try this. No, well, safety reasons maybe you don't want to try it. But if you have the extension cord fully tightened and you put a high energy appliance into it, like your washing machine or something, you'll find that it'll probably cut out or explode. So you can try it if you want.
That's it for vacuum cleaners.
Do you know the
Because vacuum cleaners have to be...
Huh?
Do you know the display was recorded?
Yeah, I do. That's why I was pausing before I said anything. Vacuum cleaners, I think, I've never actually tried it. I know a vacuum cleaner is about 3,000 watts. I don't know if that's high enough. But you're right, the vacuum cord is wound up as well. So I do wonder if you didn't unwind it and plugged it in, if it would overheat. You try it and let me know, okay? Right, so that's called Lenz's law, induction and self-induction. But now what's important for us is how do we calculate how much voltage is produced in the conductor? And that's Faraday's law. Okay. So Faraday's law says that the voltage, the EMF, the voltage, whatever you'd like to call it, that's equal to minus the change in the magnetic field over the change in time. And in fact the minus is there because of Lenz's law. The minus is only there to tell us that the direction of the voltage is opposite to the change in the magnetic flux.
Voltage or current?
Voltage, I'm saying. This formula is for voltage, yeah.
Q is the charge.
Oh, sorry, that's not a Q. That should be more like the flux symbol.
Phi.
Yeah, phi. So we'll have a look at an example of this in a moment. Just also to say, if your conductor was like the wheel that's wrapped around in the extension cord, if you had n loops, no surprise, the formula would just be this. What's wrong, Hal? You seem very distracted today. Is it because of Joshua? Do you need to move up the front? I think Joshua was happy there. Joshua? Right. So Tal, if you need to move up the front or down the back, I'm okay with that, alright? I realise you'll have to sit down by Tanish down the back, or you'll have to sit near to me at the front. Both difficult choices. So maybe behind Joshua will be best. Just to give you a little bit of vocabulary. Flux is this here, and then flux linkage is just this here. In other words, now I'm oversimplifying here. Technically it's not this, but for IFY level physics we can just take it to be this. Certainly for the exam. Flux linkage means the total flux. So if there's some kind of loop, we just multiply it by n. But I'll just tell you that that's technically not the definition, because there are at least two special situations where this doesn't work. These special situations are something you'll deal with in university. Huh? Or you'll never deal with it at all, yes. What? Right, so let's have a look at some examples now. Okay, so let's take, do you have these formulas? Yeah, okay, so let's take an example here. So let's draw my copper coil. Now I know I'm making this look like a cylinder, but it's not a cylinder. It's the only way I can draw it. It's a piece of copper that's wrapped around many times closely together, so it looks like a cylinder. But there's no cylinder inside of this, okay? It's just to help me draw it.
The red stuff is copper.
It's a copper. If you can try and draw this without the black cylinder, that would be great. No, I'll try and draw it without the black cylinder. Tal, please. This is not helping. Something. Right, so the radius of this here is, let's say, 1 centimetre. And let's say there are 100 turns. And there's a magnetic field running through this, which I'll draw in blue. So there's a magnetic field going through this. And this magnetic field has a magnetic flux density of 1 millitesla. So my 3 questions are, firstly, what's the flux? Secondly, what's the flux linkage? And then thirdly, if I remove the magnet, then what is the voltage induced? The blue, yeah, the blue there is a magnetic field. Yeah. Okay, so let's do this one together. So the first one, what formula would I need for the first one? Any ideas?
B equals phi over.
Yeah, you can just say B equals phi over A, or in other words, phi equals BA. So that would be 10 to the minus 3, and the perpendicular area that's running through the magnetic field is pi, and then it's r, which is 10 to the minus 2 squared. So this should be a pretty small number. What do we get here? 3.14 times 10 to the minus 7. Or if you want, that's 0, sorry, if I multiply that by 10, I divide that by 10, it's 0. I want to make this 10 to the minus 6. Let me just
0.014.
10 to the minus 6, 10 to the minus 6. So that is 3.14 times 10 to the minus 1 times 10 to the minus 6. Yeah, 0.314 micro Webers. Okay, I'll let you do the next part now, and then I'll do it in a moment. So I want the flux linkage.
So the unit is that Webers just for flux linkage?
It is, yeah. Actually, actually the unit, well, I'm happy with Webers, but I think a lot of books use, or not a lot of books, but some books would say Weber turns, because if you remember the formula, there's an n in it, which is the number of turns. So yeah, the second one here, part 2, the flux linkage is n multiplied the flux, which is 100. Know what I said the n was?
Yeah.
So that's 1, 2, 3. So that'd be 314 micro Weber turns.
No, because it's 9.4.
31.4.
Oh, sorry, did I go the wrong way? 1, 2, oh yeah, 31.4. Thank you. 31.4 micro Weber turns. Okay, again, let you try the last one for a moment now. So the last one is I want the voltage, which is minus n, the change in the magnetic field over the time. Oh yeah, I should give you the time as well. So let's say I remove this magnet pretty quickly. The magnetic field is gone in, let's say, half a second.
Did you give us this formula before?
Which one? Faraday's?
No, the very last one.
Flux linkage? I guess it's there.
Oh, yeah.
So I remove the magnetic field in half a second. Okay. Any answers yet?
Just 10. previous answer times 62.8 times.
Previous answer times 2.
Yes, we're dividing by 0.5, we're multiplying.
No, I don't think so.
1.1
No, not just, it's not as short as times 2.
and 616 volts.
Let's calculate it. So, at the beginning, what's the magnetic flux?
So that's 3.14.
What did I say? 0.314 microwebers, wasn't it?
Yeah.
0.314 microwebers. And then later, what's the magnetic flux? What is it? 0. Because I remove it. Yeah? Does this make sense? This is what it is at the beginning. This was part 1. And then I remove it, so this is what it is at the end. So what's the change in the magnetic flux? That would be 0 minus 0.314 webers. So the change is minus 0.314 webers. So the voltage is minus 55 times minus 0.314 times, oh sorry, there's a micro here.
What is 50?
So what?
Oh sorry, not 50, what am I talking about? 100. Minus 100 minus 0.314 times 10 to the minus 6 all over 0.5. So that would be 0.628 times 10 to the minus 4.
Sorry, I didn't get it.
How did I get to 0.5? It was given in the question. So that is 0.0628 times 10 to the minus 3 volts. 0.0628 millivolts. So it's a very, very small voltage that's produced for a very short time. Let's have a look at another type now. Okay, let me give you one to try. Sorry, do you have this taken down? Yeah. Okay, so the Earth has a magnetic field, and I actually have the value of the magnetic field here for the Earth. It's quite small. It's only going to be roughly 2, not even 2, less than 2, times 10 to the minus 5 Tesla. So, what's that? That's, well, I won't even bother. It's tiny.
Times 10 to the minus 5 Tesla.
Yeah, there it is there. And which way is north now? Let's see. Yes. I haven't given you the question yet. All I'm saying right now, Tanish, is that the Earth has a magnetic field of this strength, quite small. Now, which way is north? Let me see. The city centre would be north, which would be that way. Yeah. So which way is the magnetic field in this room going at the moment?
No, it's there.
It's going that way, actually. Yeah, it's going that way. Because the North Pole is actually where the south end of the magnet is.
But magnetic north is in the different position there.
Yeah, magnetic north is that, so the
Magnetic north is in Canada.
You're right.
that way.
Yeah.
So the magnetic field is going this way, isn't it?
Yeah.
Magnetic field goes from
North to south.
north to south. Oh, so then it's going,
I mean, magnetic poles are not same as geographical.
yes, yes. So I'm saying geographically north is that way.
Yeah, and magnetic north is there.
Oh no, we won't worry about the slight difference in the location. I know you're just saying that there's a like 10 degrees difference between the two, yeah. So hang on, north is that way, But if you remember the picture of the Earth that I drew, here, this is the north, this is the south, but the magnet is actually like this inside the Earth, south and north. Which way does the magnetic field go? South to north or north to south? North to south. So the magnetic field actually, that's convenient for us. The magnetic field goes around this way. What? Anyways, point being, the magnetic field in this room right now is going towards the window. Okay? So my question is then, I have a small conductor, only about this size. And if you think about it, if I put it here, and then if I quickly turn it around, I get a small voltage. Now why is the reason for that? Am I changing the magnetic field in this room? No. But think about it through the point of view of the conductor. For the conductor, which way is the magnetic field pointing? That way. It's going that way. Then if I turn the conductor around, the magnetic field is still going that way, but through the point of view of the conductor, its magnetic field that's gone through has suddenly changed completely around. So remember I said we could change the magnet over the conductor to make it current, or identically, if I change the conductor, it's like moving the magnet around. I mean, it's the same situation, really, just a different point of view. Okay? And so what we'll have here is, I'll go back to the question. Here's my conductor like this, and then let's say I change it really quickly in 0.1 of a second. I would like you to tell me what voltage I get in the conductor when I turn it around really quickly. So I want everybody to calculate the voltage here. I need to give you a little bit more information, don't I? Because you need the area at least. So area, it's going to be small. Let me just give you the area. I don't know, 0.001 meters squared. We'll do a more difficult example where we have to get the area in a moment, but we'll just stick with that first. No. So here we have the voltage equals minus the change in the field divided by the time, but the flux is BA divided by the time. Now, the A you can just take as constant. The B is the thing that's changing. So I can just say this is area times the change in the B over the change in the time. Now, what's the time? That's 0.1. Oh, I know the area as well, but let me put that in. That is 0.001, and the time is 0.1. Now, what do we have in here for the B, though, the change in the B? Yeah, it's minus 2 times 10 to the minus 5, minus 2 times 10 to the minus 5, because what's happening here it's 2 times 10 to the minus 5, and here it's like minus 2 times 10 to the minus 5. The direction has changed 180 degrees. So basically it's the same strength but a different direction, so a minus in front. So what's that? That is 0.01 times minus minus and a minus, so a positive 4 times 10 to the minus 5. So that's 4 times 10 to the minus 7 volts. Did we get that?
Yes.
Yeah?
Yeah.
No?
Got to. After minus.
You made a mistake or I did?
Yeah.
Okay. It's very small. So if I have a conductor here and just flip it around, I get an absolutely tiny voltage. Huh? You still get it though, yeah. Okay, let me give you another one. Can I go down? Okay. Now, this one is a little bit different because up until now, we've been changing the magnetic field. If you look at the formula, that's equal to this. And what we've been doing is we've been changing the B. But another way we can do it is we could change the area. That's another way of doing it. So let me give you an example like that. Let's see what we have. Yeah, okay, I'll give you one here. So, I have a metal rod inside. This is again the Earth's magnetic field, which, what did I say, was 2 times 10 to the minus 5, wasn't it? And let's say this rod is 1 meter long. And the rod is, the magnetic field is going this way. And it's, sorry, you can't really see it in my picture, but the rod is perpendicular to the magnetic field. So in other words, if that's north, then the rod is like this. But that's not too important, don't worry. And the rod is like a cylinder. Oh, that's just the ground. Now what happens here is, the rod is, let's say, 50 meters above the Earth, and it's dropped straight down. Now in this example here, the magnetic field is not changing, but the area is changing. Yeah, no, this is the thing. What area am I talking about that's changing here?
Between the area of the road and the Earth.
Go ahead, Charles. Yeah.
The road and the edges of the road and the Earth.
Oh, so on my picture, what is that?
Magnetic flux.
Yeah, but on my picture, what's that?
I don't know. The square.
Okay, kind of maybe have it. So what I'm saying here is, first the rod is here, and then, 1 second later, the rod will be here, and then 1 second later, the rod will be here. So the area is the area of that's what we say is being swept out in the magnetic field. It's the area the conductor makes as it moves through the magnetic field. So in other words, it's the area covered, exactly. So it's basically this area here. You can see that as time goes by, it sweeps out a bigger area. So for example, if the rod is here, at the beginning there's no area. And then 1 second later, there's a bit of area swept out and it's fallen. And then 2 seconds later, more area. Okay? So in the formula for area, when the area is changing, it's the area being swept out, or I think you said the area being covered. Okay? So what I want people to do here for me is calculate the voltage that's in this copper rod as it falls to Earth. So I think as maybe a little bit of advice maybe to get you started. No, actually I don't think I need to tell you. I think you can work this out. What's that?
What did you ask to do?
I would like the voltage in the copper rod.
What about time?
Well, this is the thing, you have to work out the time. It's the voltage as it falls and it hits the ground.
What about the mass? No.
You don't need the mass.
What's the area of the rod?
I gave you the length, which is all you need to
No,
know.
but we need to know the tangent to reach the track. We don't know the length.
But you can work it out, because I tell you how far it is above the ground. It's 50 meters high.
Ah, okay.
Yeah. So yes, your first thing to do, Todd, is to calculate the time to which this is moving in the magnetic field. So I'd like people to try this for me.
So the time is from the top to when it hits the ground. That's the time. And I remind you that the B does not change here, it's the A that's changing. How's my battery doing? Oh dear, I'll plug it in. Do we have answers? Not yet? Okay.
What is the area in there? Just 1 or 0?
The area?
When it touches the ground, when it's on the ground.
Ah, okay. So, the way you need to picture this, I'll go to the side for a moment. If you look at it like this, Tom, at the beginning the rod is here, and there's no area. And then at the end, the rod was here, and now it's on the ground. So this is like the area at the end. This is how much area is being swept out. And this is how much area is being swept out at the start. So the change in the area here would actually equal A minus 0. What's that?
I mean, you show the is.
Go back here? Yeah.
I don't understand what you mean by the area.
The area that's being covered by the rod. At the end of the journey, the area that's being covered is basically all the area.
Oh.
Yeah. And at the start of the journey, there's been no area covered.
It's a small motor.
Oh yeah, it would be small, like maybe millivolts. So if we look here, first thing I need to do is get the time. So we'll go with V squared. No, S equals. Yeah, S equals UT. Oh, I didn't tell you this, but starts at rest. Plus a half AT squared. So that's minus a half A 4.905 T squared. And the S I actually know is 50. So minus 50 if it's decreasing. So in other words, what's wrong with that? 50 over 4.905 square root is the time. So what's that, please? 3.193 seconds. Now the voltage is minus the change in the flux over the change in the time, which is minus the change in VA over the change in the time, which is minus B change in the area over the change in the time, which would be equal to 2 times 10 to the minus 5 all over 3.193, and the area here is 50 meters squared, 1 by 50. So that would be 50 minus 0. So what do you get here?
0.312.
0.313 millivolts. Yeah. So it's not much, but I mean it is something that could be measured. You could definitely measure that, but it's not much.
What's the area? Is the area right?
Huh?
Is the area right? Because
Yeah.
it's the rod is having fallen.
No, you see, this is the thing. It's not the area or the volume of the conductor. Rather, it's the area that the conductor sweeps out, that covers as it moves.
So it's not flat, not exactly flat. It's like a cuboid.
We can take the conductor as being of no volume. It's just a little thin strip of copper wire, if you want. Okay. Now, I think there is another way we could have looked at this, which just as interest I'll do down here for a moment. Sorry, do you have this here? Can I go down? So if you look at it like this, here's the rod at t equals 0, and the area equals 0. And then here's the rod 1 second later. It's made this much area in the sky as it falls. How much has it fallen? Well, the formula is S equals... Now, just to make things easy for me, because I don't have a calculator, I'll just say G is 10. I'll say it again before someone asks me why am I using 10. I'm just using 10 to make it easy for me, okay? So G is 10. So S is UT plus a half A T squared. So what's a half A here? 5. And what's the T squared? Well, I said 1 second later. So T is 1. So what's the 5 is how much it's fallen. Tal, look up please. 5 meters. So what's the area here? 5 meters squared. Now, when T is 2, 5 multiplied by 1. Yeah? When T is 2, so then the next second, or I suppose you could say, we can do the same thing here, S equals UT plus a half A T squared, so that is 20. But don't forget, I just care about how much is changing per second, okay? That's what I'm looking for here. So how much does it cover in the first second? 5. And how much does it cover in the next second? 15. So let's just do one more. T equals 3. So it falls 1, 2, 3 seconds. So S equals a half A T squared. So that's 45. So what's happening here? It goes 5, and then 15, and then what's this one here? 25, isn't it? So 5 plus 10 is 15, plus 10 again is 25. So how much area do I get per second here? 10. I get an extra 10 meters squared per second. So I could say that the change in area per second is 10. That's how much area I get per second. That's what this means. That's another meaning of it. The change in area per second, yeah?
So by changing area over time is the acceleration?
It's a type of acceleration, but to do with area. Yeah, actually, and it only looks like 10 here because I said the length is 1. If it was 2, then this would be like a 20 or something. But you're right, it does have a relationship with that. Okay, so I wonder if I get the same answer using this. Voltage equals minus change in flux over the change in time, which here is minus B times the change in area over the change in time, which here is 2 times 10 to the minus 5 times 10, which is 2 times 10 to the minus 4. What did I have previously? Where's it gone? 0.3. Sorry, so let me put this into milliamps. That'd be 0.2 millivolts. And I had 0.3. So they're not exactly the same. They're a little bit different. Which do you think is more accurate? My first method or second method? What do you think? Second method is actually more accurate than the first method. But that's not important for the exam. For the exam, they do not expect you to do it this way. They expect you to do it the first way. The reason this second method is more accurate is because I have this here, the change in area for change in time. I have that exactly right. Whereas in my first method, what I did was I looked at the area at the end and the area at the start. But that's not 100% perfect, because as you know, what happens when the rod falls? Does it sweep out more or less area or the same? As it falls, it's going faster, isn't it? So it will sweep out more area. So the change in the area per time is quicker at the bottom.
What happens if we would choose an quotation one?
Oh.
We get the same answer.
Oh yeah, so there's a little bit different. Yeah, in my other method I would get, instead of 10 meters squared per second, I'd get 9.81 meters squared per second. Yeah. Anyway, I'm just saying that the method that we use in the exam, we can actually make it more accurate by calculating the change in area per time. Okay. The best example I can give you of that is as follows. Here is a ball that's fallen to the earth. At the beginning, what's its speed? 0. Then 1 second later, what is it? Yeah, so we'll just say 10 meters per second. And then another second later, what is it? 20 meters per second. And another second later, what is it? 30 meters per second.
So increases by 10.
Yeah, that's the acceleration. It's getting 10 faster per second. Tal, please. I'm sorry if I'm boring you. Thanks. Now, here the acceleration is 10. You know what? No, forget it. It's not important. It's not important. I'm just saying that the second method is different answer to the first method because, in fact, the second method is more accurate. But for the exam, they only expect you to look at the start and at the end to estimate the change divided by the time. Okay, one last thing to talk about here. So how can you make a magnet? So in fact, to make your very own magnet, you only need 2 pieces of equipment. You need a piece of a conductor, like something like iron, and then you need a current going around it. So let me try and draw this a little bit nicer. Yeah, no, it's not called that. Maybe someone knows what it's called. So you have an iron rod, and then what I do is I wrap a current around it like this, and the current goes in here, out here. No, does anyone know what this is called?
I know the name in Russian.
Well, maybe it translates well to English. What is it called in Russian?
I don't know what it's just like.
No. Tell me the Russian for it. Yeah, no, it's not the same. Yes, it's called a solenoid. Yes, it's similar to the Russian. Solenoid. Solenoid, okay. When you have a current wrapped around a piece of iron, you can actually make a magnetic field. Sometimes in the exam they ask you to draw this. So let me draw the magnetic field that you make in blue. So it's a bit like making a magnet that looks like, well, actually I can't really draw it, but it goes, magnetic field goes to the right here. In other words, the magnetic field, the way to remember it for the solenoid is it goes in the same direction here as the current is going in.
North and south.
Yeah, so the magnetic field, remember, goes from north to south. So Joshua, it's a bit like you have a north here and a south here, and your magnet's going like that.
Only iron ores.
No, iron just works really well and it's not too expensive, but basically I suppose you could do with copper or any type of good conductor. Steel, yeah. Steel would probably be the cheapest way to do it. But in fact you could even use the graphite in your pencil is actually a good conductor. So you could wrap a current around the graphite of a pencil and you could make it into a magnet. Huh? Or a nail, yeah. So this is called a solenoid. I mean, the only thing they can really ask you in the exam about this is to draw it. So there you go. What are you doing there, Joshua? You're looking for a slap, aren't you? Yeah, that's what you're doing. Okay, did you draw that? Yeah. Now, remember earlier I did my example of the conductor moving around like this in the magnetic field in the room. And I said, oh, the magnetic field is changing. But I cheated a little bit because not only is the magnetic field changing when I turn it around like this, but what else is changing? No? The area as well. Because it's sweeping out an area in the magnetic field. But I didn't need to consider it really, because remember, what I did was I looked at it through the point of view of the conductor. So through the point of view of the conductor, if you can imagine you're a conductor right now, you're standing here pointing north, and then what happens to your magnetic field? It looks like it quickly rotates around you. So through your point of view, there's no change in the area because you're stationary, okay? But to someone looking on the outside, it looks like the conductor swept out some area in the magnetic field, and the magnetic field didn't change. So what I'm saying is you could look at this problem two ways. Firstly, through the point of view of the conductor, it doesn't move, but the magnetic field switches around. Or through the point of view of the magnetic field. The magnetic field doesn't move, doesn't change in this room. Instead, the conductor sweeps out some area. So you have two ways to look at it. Now, why am I talking about this point of view stuff? In fact, it actually is important, and it'll be important for what you do in university. But a lot of things in physics, you find that you get the same answer if you look at things through one object or through the other object. So if you look at this problem as the magnetic field, or if you look at it as the conductor, you get the same answer. So I don't want to talk about this too much, but that's to do with relativity. I don't know if anybody knows that word. That's what I'm saying, it's to do with. So what I'm saying is, the conductor can view it as a problem in which the magnetic field changes, or the magnetic field can look at the conductor changing its area inside of it. Okay? But don't do both. Don't say the magnetic field and the area changes. Okay? Yeah, they get the same answer, or at least roughly so.
In general, it's special.
No, not even anything to do with special or general, just something before those. Okay. So, I think what I'll do is, I'll let you work on these questions. There's not many of them. You should get them finished now. And I have the answers at the back, so you can check them as you go along. This comes up in section A and section B. It's not very difficult. In fact, it's pretty straightforward because there's not many formulas. We basically deal with two formulas for this topic on field. The first one is flux equals B over A. Sorry, flux equals B multiplied A, and voltage equals minus the change in flux over the change of time. And if it's a coil that's wrapped around n times, we just multiply our flux by n. Okay, so I mean, compared to other parts of the course, there's not that many formulas. Yes? Yeah, that was what we did previously. That is the force on a charge moving in a magnetic field. And then what's the one for a charge moving in an electric field? QE. Yeah. That was the previous topic, yeah. So, we just have one lesson left, and then we have field finished. So what we'll do next time, not next time, because tomorrow we're going to do revision. Thursday we have a double class, don't we? Yeah. So tomorrow we'll do revision. So next week we'll do the last... Yeah, hot paper. Next class we'll do transformers. Optimus Prime, Decepticons, all of them. Yeah. Maybe one for down or two?
I was just going to a picture of it.
Alright.
Can I do it now?
Yes, go ahead. Okay, so work on these, and whatever you don't finish at home. But look, if you finish these and have no trouble, then I won't bother going through the trouble of doing the answers in the next class. But if you have problems, that's okay, I can do them in the next class, okay? But I would hope that there wouldn't be many problems. Yeah?
Just one for you.
Yes. Huh? That is the force. Did you miss that class or something? You did, didn't you? That's the force on a charged particle in an electric field. Why isn't that soon here, you know?
Too much drinking.
Yesterday, yeah, they didn't pace themselves and now they're regretting it.